So good afternoon, everyone. I'm very happy to welcome Dr. Reza Younesi. So I will read a few words on his journey in. Yes, I have to be on screen. Yeah. So Dr. Reza did his PhD in Uppsala University. He then moved to Technical University of Denmark, close to Copenhagen. And then he's now associate professor at the Helstrom Advanced Battery Center at Uppsala University as well. So he's quite used to cold weather. Was hoping to give him a bit warmer welcome here, even though it's quite cold lately. And his research is focused on interfacial reactions and material developments for both sodium and lithium-ion batteries. And he's also board member of Altruist AB, a company founded in 2017 and specialized in producing sustainable cathode material for rechargeable sodium batteries. So please, Dr. Reza Younesi, the floor is yours.
Thank you very much, Alex, for the nice introduction. So it's my honor to be here at ICMAB Center, which is known as one of the best research lab when it comes to batteries. So it's a bit challenging also to come here and talk about batteries because there are so many experts here. So I hope you will learn something after this presentation, and I hope you will enjoy it. And then, of course, I would be happy to get questions to discuss. So as Alex said, my name is Reza Younesi, and I'm associate professor at Uppsala University, working on different types of batteries, but mainly sodium-ion batteries. So I'm going to go briefly about, let's see if this works. Yes, a brief introduction about my experience and background. So I did my bachelor in Iran. So I'm coming from Iran, but I moved to Sweden almost 16 years ago. I did my master in nanomaterials at CATF in Stockholm. Then later I moved to Uppsala and did my PhD on lithium-ion at Uppsala University, and then later to Denmark, DTU, where I did my postdoc, and then later I started my own research team at Uppsala University since a few years back. So I have been very lucky to have a number of excellent supervisors and advisors through this journey, from my bachelor to master to PhD, and later to postdocs. So you see their names and photos here. And then you see the photos of few people in the sodium team that we have in Uppsala University, trying to understand sodium-ion batteries. So feel free to interrupt me if you have any question anytime. So for those of you who don't know where Uppsala is, I put the map here that you have Sweden, and here is Stockholm, and then it's almost 70 kilometers towards north from Stockholm to Uppsala, and you have the airport, Arlanda Airport, which is the main airport of Sweden, somewhere between Uppsala and Stockholm. So it's very convenient to travel to Uppsala, and there are so many trains connected, so it's very well connected to Stockholm. So it's actually it's the fourth biggest city of Sweden, but it's growing very, very quickly also. So it's one of the oldest city in Sweden, and it has almost 40,000 students. It's very student city, and the total population in Uppsala municipality is about 200,000. It's known very much. Uppsala city is known very much for its university, Uppsala University, which is the oldest university in Nordic countries. And within this university, there are a number of different fields and programs and different campuses. One of them is this called Helstrom Lab, which is almost 25 years old, if I'm not wrong. And then you have several engineering faculties and departments there. And within this Helstrom Lab, there's a center called Helstrom Advanced Battery Center, which was launched in 2000 almost. This was launched by Josh Thomas and Torben Gustafsson, and Christina has been leading this center in recent years. So these three were basically the starting people. Josh started the battery group. He was working on batteries where no one was interested to batteries. So he's coming with the same, his generation of people who were pioneers on batteries like Stanley Whittingham and so on. And then they decided to have this battery center in Uppsala. And some of you know Christina because she is leading Battery 2030 activity and many different research activities in Europe. So this is the battery center in Uppsala. If you look at the current picture, we are almost 90 to 100 people coming with different backgrounds, mainly chemistry, physics, and some engineering. We are 7 PIs, or we call it senior scientists or whatever, and there are 2 more under recruitment, 2 research engineers, 25 postdocs, and almost 40 to 45 PhD students. So it's a relatively big group. It is definitely the biggest group in Nordic countries and perhaps one of the biggest in Europe. We are also coordinating 2 major activities. One is Battery 2030, which is by Christina, as I said, and also BASE, which is a center started almost 1.5 years ago, and it is in Sweden, batteries in Sweden. So there are people graduated from this group going to Swedish and international industry and academia every year. And if you look at the research in this group, as I said, most of us are coming with material science or chemistry and some physics background. So we do look at the battery components, anodes, cathodes, electrolytes, and all the components that you find inside the battery, binder, and so on, to try to understand chemistry and material science of those components and try to make them better, to improve the performance, but also understand the chemical and electrochemical reactions. We do work on battery concepts like safety, aging, new chemistries, including sodium, but also a little bit on lithium sulfur, lithium oxide, and so on. We also do have some activities on online characterizations, sensors, modeling, electroanalytical methods, and so on. So this is mainly the research activities at Uppsala. What you see here is, again, as I said, is very much materials science and chemistry motivated. We don't, for example, we don't work that much on cell level or package level yet. Of course, we do some aging on commercial cells, but still we are not really into the understanding of BMS, for example, or package level. So we are more into materials and chemistry. And within this center, what did happen? Yes, I was here, sorry. And in this, within this center, as I mentioned, I started a small team working on sodium-ion batteries since 2015. And our focus in this sodium-ion battery team is to understand aging in sodium-ion batteries and how different that is compared to lithium-ion batteries, compared to aging lithium-ion batteries. So we do use different analytical techniques in the lab, but also we do use a lot of synchrotron-based spectroscopy at synchrotrons in Sweden and also in BESI and DESI in Germany, in Diamond and ICIS in the UK, and also in Japan and the US. We do also work on development of new materials for sodium-ion batteries. That is one of the main core activities that I will talk about today. And there has been a spin-off company called Altruist from this group where we try to commercialize, to work on commercialization of sodium-ion batteries. So I will talk a little bit about that also. So the topic, maybe I didn't say it clearly in the beginning, that the topic of this talk is to explain the challenges and opportunities with sodium-ion batteries from the lab and also to the applied commercialization. So what we have learned in the last few years in the lab and also what we are learning now, moving towards commercialization of sodium-ion batteries. So I thought to put this slide here, which I'm sure many of you know that batteries are growing. This is clear. There is no question about that. perhaps the growth rate today is much faster than what people were expecting maybe 10 years ago, 15 years ago. Everyone was, I mean, I think everyone agreed a few years back that there will be growth on battery industry, but maybe no one expected such an increase in battery production. So the picture of battery production is evolving very quickly, no question about that. And it seems there is no turn or U-turn on that. This is going to continue. But that means we will actually need more and more materials used inside lithium-ion batteries, because the growth that we mentioned here so far has been very much on lithium-ion battery. So the elements that are used in lithium-ion batteries are needed more and more. And those, you can see some of them here: manganese, lithium, cobalt, nickel, graphite, aluminum, and copper. Those are the common elements used in lithium-ion batteries. So it's a very clear increase in the demand for those materials. What you can see here, this picture is for EV. So the main push is coming from transportation industry, but it is affected by portable devices and stationary storage industry also. Perhaps people would consider stationary storage a small market up to even like 4 or 5 years ago, but we do see clear sign that the stationary storage is changing very, very quickly, especially with all the politics nowadays and the war by Russia. There is more clear demand for local energy production and storage to be more independent from gas and oil. So this is a pressure from different countries, industry, and society to produce more batteries. That means we need more elements to produce lithium-ion batteries. But the problem is that if you look at those elements used in batteries, some of them are not available everywhere. Lithium is mined in few countries. And also, remember, it's not only about availability, but also it's about production possibility. So the problem with lithium mining is that it takes many years until the day you start to do mining to the day where you really produce lithium. It takes many years. So there will be a time gap. Cobalt is a problem that everyone is aware of, that 65% of cobalt is coming from one single country, Congo. And graphite, natural graphite, is coming mainly from China. And nickel is an interesting example that a few years back, I still remember a few years back, when we were discussing this picture, people were saying that, oh, nickel is fine, we have enough nickel. Which, of course, nickel is much less problem compared to cobalt. But you can see that how different political events can influence the market and the price. So Russia is one of the main exporters of nickel, and you can see that the price has been affected very much in the last few months. So there's a clear push that we need to move towards elements that are available everywhere. So naturally abundant elements to produce batteries for different applications. Of course, that doesn't necessarily mean that we're gonna have high energy density batteries to replace lithium-ion batteries. The goal is not to replace lithium-ion batteries, but rather the goal is to have different chemistries or different batteries for different applications. So if you look at the market so far, we have had basically the same chemistry, lithium cobalt oxide versus graphite, for every single application, no matter it's cell phone, laptop, electric vehicle, or even in Uppsala now there are some containers for stationary storage, and those are like lithium-ion battery inside those containers. So this is the problem. We have been using the same chemistry for every single application, while we need to move towards more abundant elements to produce different batteries, different energy density, different price, and for different applications. So this is happening for sure, that we need to move towards this green area to produce batteries that are competitive to lithium-ion batteries, but also they are based on naturally abundant elements, so they are much more sustainable in long term. And that's the motivation to work on sodium-ion batteries, magnesium, calcium, potassium, and so on. They are all have this advantage of naturally abundant. But there are other factors also, of course, come to play beside natural natural abundancy, and that is cost, the production, not only the cost of raw materials, but also the production cost. The unique thing I would say with sodium-ion battery is that they call it drop-in solution. So it's the same factory that is producing lithium-ion battery can produce sodium-ion batteries tomorrow. There is no need for major changes. That is the advantage with sodium-ion batteries. So you can see that abundancy of sodium compared to lithium is affected to the price that you see here. The y-axis is the cost of carbonates. So sodium carbonate is much cheaper than lithium carbonate. And the importance of this is that carbonates and hydroxide are used to synthesize cathode material. These are common precursors to synthesize cathode materials. So from the precursor to cathode material, you can see that you can gain actually with sodium-ion batteries to reduce the cost. But there are differences also between lithium and sodium. Some of them are against sodium-ion batteries. So the potential of sodium-ion batteries is 0.3 volt higher than lithium. And the potential of reduction and oxidation of metallic sodium is 0.3 volt higher than metallic lithium. And that can play against sodium-ion batteries when it comes to the cell voltage. Sodium is heavier, of course. Sodium atom is 3 times heavier than lithium. But remember that we are not going to use only lithium and sodium atoms inside the battery. So when you go to the battery, there are other components. So you're going to use lithium in the format of lithium cobalt oxide on the cathode side, and then you're going to have graphite on the anode side. You have separator, casing, and so on. So all those added mass will add to the mass of the battery cell, which means the difference is not going to be necessarily 3 times. So depending on what kind of lithium or what kind of sodium chemistry we are talking, the energy density can be competitive. So when we say lithium-ion batteries, it's important what kind of lithium-ion batteries we are talking about. If you look at the state of art today, LFP-based batteries have definitely lower energy density compared to NMC-based batteries, but then sodium-ion batteries are becoming competitive to LFP-based batteries in terms of energy density. There are also differences if you go a bit more details when we look at the atomic size or ionic radius of lithium, sodium, and potassium. It gets bigger from one cation to the other one, and that will influence the conductivity and viscosity. It does influence the charge density around cations, and that does influence the interaction between the cation and anion. And that leads to differences in conductivity and viscosity. So in one way, they are very similar, but on the other way, we can see that these differences will bring challenges, but also will bring opportunities to develop sodium-ion batteries. So with this introduction, I'm going to go now to different research examples that we have been performing in our lab at Uppsala University. So when we make batteries, of course, similar to lithium-ion batteries, there are 2 electrodes, negative and positive electrode, current collector on each side with a liquid electrolyte between. So it looks like this, which I'm sure many of you know that. There is a thin layer of separator with a liquid electrolyte between the electrodes. And then we either make pouch cells or pouch bag or coin cells like this to study different electrode materials or electrolyte material. So one of the first study actually we started a few years back to understand aging in sodium-ion batteries was to look at SCI in a bit more details to understand SCI dissolution. So for those of you who don't know, when you make batteries, typical lithium or sodium-ion batteries, the negative electrode potential is very low. It's beyond the stability of the liquid electrolyte. That means the liquid electrolyte will be decomposed to form a solid electrolyte interface. This is called SCI. So it's very important phenomena to make the battery kinetically stable. So the batteries that we are using, they are not thermodynamically stable. So we need to make them kinetically stable. So this is done by this SCI. This, of course, is a very schematic picture here. In reality, SCI is very thin layer, just few nanometer of inorganic and organic species. So this layer is supposed to be electronically isolating. So it should not allow any electron diffusion or electron transfer, but at the same time should allow ion diffusion, ion transfer from the electrolyte to the electrode. Another important aspect which sometimes is neglected is the solubility of this SCI. You form this SCI in the cost of irreversible capacity in the beginning when you start the battery. So this forms as via irreversible charge. So you consume electrons, you consume electrolyte to form this layer. So it needs to be very stable because you don't want to form it again. That means it should not be dissolved in the electrolyte. The solubility of SCI is a topic that we try to understand a little bit more in the last few years. So here you see again a schematic of a battery where you start to have reduction on the anode. That's when the solvent and salt molecules will be reduced on the anode and they form the SCI. So this SCI should be stable, as I said, but when you stop the battery, what can happen is that this SCI may be dissolved back to the electrolyte. And that's a problem, as I said, because then that means you need to reform SCI again if it's not passivating. The same thing can happen actually when the battery is under performance, when you are discharging or charging, the same thing can happen, and this SCI dissolution may cause capacity fading. So the problem with SCI is that you may form cracks, you may allow solvent diffusion through this SCI, which will lead to more irreversible capacity. And that's why we want to have it very, very stable. The other reality is that when these SCI species are dissolved, at some point the electrolyte will become saturated by SCI species. So we try to understand when is that point that the SCI actually is, the electrolyte is saturated by SCI species, and is there any way to influence that to make the battery more stable? So the first test we did was on top left, you see galvanostatic cycling of negative electrode material, few cycles, then pause, few cycles, and pause. So we have been trying carbon-based anode material, high surface area carbon-based material, Super B, for example, but we have been using also low surface area metallic gold and platinum. So we have been working on model system, but also on real system using either low surface area hard carbon or high surface area carbon black. So what we can see here is that, and then what we do basically, cycle, pause, and then we can see how much capacity is lost during this pause. So what we learn here is that this capacity loss is dependent on the square root of the time. We can also see that this capacity loss is very much dependent on the electrolyte volume. So there is a linear relation between that. And from that, we concluded that there is a CI dissolution, which basically leads to such a capacity fading. So you give it time, CI species will migrate to the electrolyte. So there is a diffusion of SCI species from the SCI to the electrolyte. We also did some mass spectroscopy measurements. I'm not going to go details of all the peaks here, but what you need to see here very briefly is that if you compare the pure electrolyte to this sample in the middle, which says before storage, you can see that, of course, the cycled electrolyte has more peaks as we expect. There are more things formed in the electrolyte. But one thing is interesting for us is before and after storage, we do see differences. The intensity of these peaks, for example, is changing. These peaks here also are changing. There is a little bit change here. So things are happening before and after storage. That's also another confirmation that it's a dynamic system and there is changes in the concentration of a species inside the liquid electrolyte. We also try to do ICP to understand how much of SCI species we can dissolve in the liquid electrolyte. The problem is that, of course, if you look at real electrolyte, there are so many peaks. It's extremely difficult to see what are these species. That is the challenge. but we can imagine some of the species, as many literatures have shown. Lithium fluoride or sodium fluoride are common SCI species in lithium and sodium ion batteries or carbonates. And this list can continue actually to organic and so on. So a few years back, actually, we saw this interesting paper by this group here, where you guys measured the solubility of these species in water. Then we followed this work, and actually we measured the solubility in organic solvents. What we could learn here is that the solubility is, of course, much lower compared to water, but there are also differences. It's not like that we say that if you go organic, then the solubility is the same. There are big differences between PC and ECDC if you look at the solubility of these species. And also there is a clear trend that if you compare on the same solvent, if you compare sodium species compared to lithium species, we can see there is much higher solubility of sodium species. This is again another indication that solubility of these components, if they are in the SCI, that's going to be challenged. This might also indicate that actually we are more dependent on forming organic species in the SCI of sodium compared to the SCI of lithium-ion batteries, because we want to reduce the solubility. So if you go with inorganic, the problem is that most inorganic species in sodium-ion SCI are more soluble compared to lithium-ion SCI. So since then, we have been using many different cycling protocols and many different battery systems. As I said, we have been using carbon black as a model system with high surface area to generate a lot of SCI and accelerate SCI dissolution, but we have been testing hard carbon and also metallic gold and metallic platinum as the negative electrode substrate. So we have been using three different protocols to look at if we cycle the battery for a few times, keep it at low potential. The point is that at such a low potential, you're going to have continuous SCI formation. There is also a possibility of having sodium ion trap, because if you keep the battery here at that potential and give it time, sodium ions will diffuse from top surface of carbon particles to the core of carbon particles. And there is no guarantee that actually you manage to extract all those sodium out when you charge the battery. We have been also doing this pause experiment at high potential, where there is at 2 volt, for example, which the battery goes by itself, it goes to almost 1 volt. That means there should be no SCI formation at such a potential. There we can look at only and only SCI dissolution. So we still try to understand this more, how SCI dissolution is affected by chemistry of solvent, salt, the cycling protocols, the temperature, and so on. Some of the results that we have got so far indicates, of course, as expected, this SCI dissolution is very much dependent on the salt and solvent chemistry. Here you see we have tested 3 different salts, PF6, FSI, and TFSI, in 3 different solvent mixtures, either ECDC or ECPC or ECDME. What you see here is that no matter what salt you use, ECDME provides the lowest capacity loss due to this SCI dissolution. So that's one of the conclusions here. But we can see also for the same solvent, there is influence by the salt. So for example, if you go for ECDME, we can see that there is a difference between TFSI or FSI or PF6. And TFSI in ECDME is giving the lowest capacity loss due to SCI dissolution. Of course, this is one of the components. This is one of the aging mechanisms that we are focusing on. This doesn't necessarily mean that this electrolyte is the best electrolyte for sodium-ion batteries. No, who knows what would happen if you put this electrolyte in a full cell with so many different aging mechanisms. Is this really stable on the cathode? We don't know. So the focus of here is only and only on SCI dissolution. But this is the way to basically to exclude at least some of the parameters from such a complex system and try to focus on one parameter or one aging mechanism. The next step for us was to say, if we believe that, or which we have shown that this SCI dissolution is a problem, So we get a species from SCI going to the liquid electrolyte. The question is that, can we actually add those species into the electrolyte to prevent such a dissolution, basically, to saturate the electrolyte by a species that you expect to be dissolved and stop the SCI dissolution. That's what we try to do. And then we look at these two different components, sodium fluoride and sodium carbonate, which, as I said, they have different solubility in PC and ECDC. Clear difference that you can see that they are much more soluble in PC compared to ECDC. So our expectation here is that saturation of PC electrolyte by these species should have much more visible or detectable influence compared to this solvent compared to ECDC. So we saturated the electrolyte and we did XPS on the negative electrode. What we could see that actually the red ones are PC electrolytes, unsaturated and saturated with sodium fluoride. And when I say saturated, I'm talking about like ppm level. So what we did, basically, we used this amount to saturate the electrolyte, and then we filtered the extra remaining one. So we can see that actually there's a clear difference in PC electrolyte. When you saturate the electrolyte, the SCI on carbon material, and this is fluorine spectra of a carbon anodes, we can see that the SCI is changed, or the surface layer composition is changing. Now we suddenly have sodium fluoride peak in PC, which is saturated with sodium fluoride. While in unsaturated, we didn't have that in such a high degree. It was a small peak. But we don't see such a change in ECDC electrolyte. That means the addition of sodium fluoride to ECDC basically didn't do anything, at least to the fluorine spectra, while it did major changes to the fluorine spectra of the PC sample. So we could see that from here that we expect that the capacity loss will be smaller if we add sodium fluoride to PC, and that is exactly what we did. If you look at the red ones here, this is the control sample, and then this is saturated by sodium fluoride. We can see that there is lower capacity loss when we go to saturated. While if you look at ECDC, we don't see major difference. Actually, it became a little bit worse when we added sodium fluoride to the electrolyte. On the other hand, we didn't see such a thing with sodium carbonate. This is still puzzling. We didn't basically see any advantages of sodium carbonate to PC electrolyte, which our conclusion from this result was that we don't expect sodium carbonate perhaps in the SCI from the beginning. So the addition of such species didn't really help to saturate the electrolyte to decrease the SCI dissolution. But this is a way for us to, or it's a strategy to try to mitigate the SCI dissolution. So this was basically a quick overview of one of the projects that we have been doing on understanding of aging in sodium-ion batteries. But as I said, aging is such a complex topic. There are so many different aging mechanisms, and we are focusing on only SCI dissolution in this work. So I'm going to continue a little bit more with this section, materials development, and then we will end with Altruist. So when it comes to material development, what we did is we had a relatively huge study a few years back looking at 13 different solvents for sodium-ion batteries. So the same electrode materials, this is precision white versus hard carbon. What we did was we tried to reinvestigate electrolytes for sodium-ion batteries. None of them is new. These electrolytes have been studied if you go many years, but for different reasons they were stopped. We didn't do that much research on these electrolytes for lithium-ion batteries because carbonates, including ECDC, DMC, and so on, perform very well. So many of these solvents were not interesting for many years. So what we try to do is to have a new look at these electrolytes to see if we get any advantages with these chemistries. And the reason behind that is that, as I said in the beginning, lithium-ion and sodium-ion batteries are not necessarily the same when it comes to especially electrolyte properties. There are similarities, but there are differences. So in this huge work, which I think this is actually one of the largest battery paper that you will find, I promise you. If you go to this one, it is so many pages and you get tired of it. But I had a suggestion actually to split this maybe to 2 papers, but Ronnie Morgensen was one of the authors. He really wanted to have it as one paper to have his sign on it. And I said, okay, up to you. So it's a really long paper. We did actually initial evaluation based on the conductivity of electrolyte. Sodium PF6 was used in all these solvent mixtures. We did some initial cyclic voltammetry, ionic conductivity measurements, and initial galvanospheric cycling. And based on that, we decided to go where? Either with the solvent was promising, so we tried some additives also to the solvent to optimize the system, or we could see that there is need for actually co-solvent because the conductivity was low or the viscosity was too high. So we took 2 different approaches to look at these electrolytes. I'm not going to go to the details of all these electrolytes here. It takes a long time, but I thought to put just a snapshot of the results where you could see that some of these electrolytes actually, like sulfonate-based electrolytes, they do give quite high Coulombic efficiency on the first cycle and also relatively stable cycling. And some of them, as I said, have been neglected because they are not that interesting for lithium-ion batteries, but they may provide actually opportunities for sodium-ion batteries. The other step that we took was actually from this work where, where everything was based on PF6, we tried to move towards fluorine-free electrolytes. And what we found that actually, if you look at, there are only a few options if you think about fluorine-free electrolyte salts. One is perchlorate, which there are still arguments around that, whether it's safe or not. The other option is BOB, which lithium BOB has been a common lithium salt for lithium-ion batteries. But when we look at literature, we could see that there is no papers actually using sodium BOB. There was only one paper by Stanley Whittingham showing the synthesis of sodium BOB and crystal structure. And this was published in 2003, but no electrochemistry, no battery cycling. And then we found that the reason is that sodium BOB is very much insoluble in common solvents, like in ethers, carbonates, and so on. Then we were just by accident, to a large extent, we were lucky to find out sodium BOB actually is soluble in phosphate-based solvents, including TMP, TEP, and so on. It is soluble in NMP also, but NMP, of course, is not that interesting solvent in terms of toxicity. So we have been working on phosphate-based solvents, TMP and TEP, together with BOB, and we show that this electrolyte actually can be used for sodium-ion batteries. It provides relatively high conductivity or acceptable conductivity of 5 millisiemens per centimeter at room temperature. No HF, it's low cost. The synthesis is relatively easy. There is no need for fluorine, and it's non-flammable. Excellent. So this is the main electrolyte that we have been focusing in the last few years. We, of course, the non-flammability in this type of test that we are doing here, which is a common way that people do in literature, is the first step to understand if the electrolyte is safe or not. But that doesn't necessarily guarantee that the battery is going to be safe. So, of course, the next step for us is to take such an electrolyte in a real battery. We have been testing in prototypes, but in a real battery, and do safety tests in larger scale to see what kind of gases form and so on. This was basically what I wanted to say on the liquid electrolyte. The next, which is the last piece, is on the cathode material, which I put it last because if you think about it, we had no plan to work on cathode materials when we started the sodium group. Our main focus was on liquid electrolyte and the anode, the SCI. But the problem was that we had to use sodium metal as the counter electrode. And we knew that sodium metal is not a good option because you get a lot of side reactions, the electrolyte become contaminated, and the results are not reliable. So we were looking at literature to see, can we have a good cathode material to use just as a counter electrode, something similar to LFP with a very flat potential, and use it as like LFP in lithium-ion batteries, but something like that for sodium-ion batteries. Then we happened to see this paper by John Goodenough on Prussian white, which looked excellent because it showed two flat plateaus, relatively high capacity, 170 milliamp hour per gram, with two flat plateaus, which meant we could use that as a counter electrode. That was the main idea in the beginning. But then what we found was that the synthesis was actually challenging. This was high temperature, high pressure synthesis that they showed. And then we said, I mean, this basically motivated us to find easier way, because we were lazy, to find an easier way to make this material. And we were lucky that happened actually, that we found a method to synthesize this material with at room temperature or a slightly elevated temperature with no need for extra high pressure and so on. And that was when we launched this spin-off company called Altruist in 2017. So it's the core business of this company is to produce Prussian white cathode material in larger scale, low cost, with no need of nickel, cobalt, or copper. And it has got this commercial trade name also. We used FENOC as a trade name for this material. So as I said, it has two flat plateaus. That's the interesting part with this material, relatively high capacity. The potential of average is almost 3.1 volt. You can make actually big particles and cubes of this material, which is advantage. It is relatively, ion diffusion is relatively fast. And as I said, it's all based on naturally abundant elements. The challenge with Prussian white is that when you go to literature, there are so many different synthesis methods, there are so many different qualities, and that you can see that people are showing many different results. And that was also a bit confusing for us in the beginning, while we learned that the performance, electrochemical performance, is very, very much dependent on how you make the material. The details of synthesis are very important, and how you treat the material, storage, cycling, battery assembly, those are all very important to get good results. And then it can, the interesting thing with this material also that the color can change depending on how much water you have or what is the crystal structure. So we started with a smaller scale in the lab, of course. We were up here to 2 liter, I think, when we started. Actually, maybe this is something that we should look at it from a commercial point of view. So then we discussed with different people in Sweden to see if this is a good idea or not. Then Altruist was launched, and then we moved slowly to higher and higher scale. So what Altruist started, when we started Altruist in 2017, we got this 100 liter also to increase the production. And this is continuing with 100 liter and 600 liter containers to produce Prussian white, high quality Prussian white. The next step, which is happening now, is to have the real factory, which will be with a production capacity of 2,000 tons per year. The site is decided, the contract is signed today, more or less. So there will be construction of the factory in upcoming days, basically. So it's expected to be finished by early next year with this product, with capacity of 2,000 tons of Prussian white. And that will enable 1 gigawatt hour production of sodium-ion batteries. That's where Altruist is now today. Of course, there have been a lot of challenges, but there have been a lot of interesting learning procedure also. And then if you look at what I have should said maybe is that what we did also where we were here to relatively larger scale production, we also started to make bigger battery prototypes, not only small coin cells or pouch cells at the university, but also we started a joint project together with a company called Life Size, where they can produce battery prototypes. So we have been, in the last few years, we have been making 1 amp hour to few amp hour cells. and also to smaller scale cells, but with really, really high mass loading electrodes to have identical condition to commercial batteries. So here are a few examples. So on the left, you see a battery prototype, which is based on hard carbon pressure white, water-based coating. Everything's water-based coating. There is no NMP here. And it's cellulose-based separator. And on the right, you see 5 identical or similar cells with this electrolyte that I mentioned, sodium bulk in TEP. They have been cycling now 400 cycles almost, with a rate of C/3 and with retention of almost 70% now after 400 cycles. The interesting thing with the station is also that we don't necessarily, of course, we would like to increase the number of cycles. That is the highest priority now that we are working. We need to reach to 1,000 cycles, but we do see the possibility. But the good thing with batteries for a stationary is that the state of charge can be relatively low at the end of cycling, and that is acceptable for a station. While when it comes to automotive industry and electric vehicles, everyone would like to have 80% or maybe 70% of charge, state of charge, even after several hundreds. So that's where we are. And of course, we haven't been the only one trying to commercialize sodium batteries. There are many different players. I'm sure some of you have heard about Faradion, a UK-based company, which they were the first, if I'm not wrong, or one of the first starting commercialization of sodium-ion batteries. But the company was sold to Indian company very recently. Then we have Tiamat in France, working on vanadium-based cathode material to commercialize. And then Haina in China. They have been working on sodium-ion batteries for a few years. And Natron in the US, where they work with the limited potential cells. So the picture is evolving very quickly, and we expect that there will be more and more players, which is good, I think, for everyone to make sure that sodium-ion batteries are becoming a reality. The biggest influence, I would say, was by CATF last summer, when they came out publicly announcing that they're going to produce commercial sodium-ion batteries. This was a big advantage for us because it was right timing, and also they said that they're going to use actual pressure white in their sodium-ion batteries. So this was revealing for us to see that the big company is going to use the same material that we have been pushing for a few years. And this has been very helpful, of course, to all sodium battery companies to convince industry to produce sodium-ion batteries. What the latest thing that happened was just a few days ago, March this year, where Altruist got almost 10 million euro in aid funding to make the factory happen. This factory that I mentioned, which will produce 2,000 tons per year. There have been a number of investors, but 3 leading investors are Northvolt, which I'm sure some of you have heard. It's a gigafactory in Sweden. It started a few years ago, under construction, but they have produced their first lithium-ion cells a few months ago. And then Molindo Energy and EIT Energy. So with that, I would like to thank you for your attention and listening to this presentation. And I would like, of course, to thank the students in sodium team. All these results are generated by the PhD students, postdocs, and master students. And also to the funding agencies, both Swedish funding agencies, but also European ones. Thank you very much.
Okay, so thank you very much, Reza. That's very nice to see some success story, entrepreneurial success story for non-lithium batteries.
Yeah.
So the paper is now open for questions. We also might receive questions from the Zoom attendees. So you can just raise your hands and we'll put you online. So do we have physical questions or yes, Rosa?
Well, I have some which are not really scientific, but on the scientific side, the measurements and the solubility of the SEI seem very tricky to me. So I wanted to, whether you could further comment on this, because as you were, you mentioned a little bit on the influence of the amount of electrolyte. So how tricky was it to do these experiments and then have enough electrolyte to analyze? Because I guess that for this, you would need to add a lot of electrolyte, but then the solubility will be enhanced. And how these amounts that you were testing compare with the real amount of electrolyte that you have in a cell, which is smaller, which would, in theory, decrease the solubility. So,
Sure, good question. The way that we made the cells, these are still pouch cells, coffee bag cells, so that means it's not a beaker type of cells with a huge amount of electrolyte. So it's still separator, but we did have 3-4 different volumes, which of course for the following characterization where we want to do, for example, solubility, ICP, or mass spec, we use the highest volume, as you said, to let us be able, basically to enable us to do characterization, because if you do a small volume, then it will be impossible to do mass spec. And as you said, all these volumes are still much larger than what you have in a real cell. I agree, but the point here is that we want to actually exaggerate the problem. We want to accelerate aging. So the higher volume of the electrolyte is good for us to see the issue faster. It's the same thing with the surface area of electrodes. We have been using high surface area carbon black, where we can see that, of course, SEI dissolution is much pronounced if compared to low surface area carbon-based material. So in reality, this will be much less problem if you go to real cell. But since we wanted to accelerate the issue, we went to relatively larger volume and larger surface area. So whatever we find here, we think, of course, will be less of a problem when you go to real battery. But still, we think this is perhaps one of the aging mechanisms that is actually leading to capacity fading in commercial cells as well.
Even if you have less electrolyte.
Exactly, yeah.
And then I had a couple of questions about the company and your business model. So do you aim at also producing cells, or ideally you would supply the active material to the cell manufacturer? And also, how is the patent landscape? So how can you protect what you do? Because there is, as you mentioned, some papers, there is a lot of literature, and how is with respect to CATL and so on?
As we are talking today, this is the model that we are following today, which may change later, is to actually to sell material, whether it's cathode material or the electrolyte, to any possible company. So it's open to anyone that would like to commercialize sodium-ion batteries. But also we are following production of sodium-ion batteries together with other producers. That means Altruist itself is not producing, is not aiming to produce sodium-ion batteries by itself tomorrow, because that's huge investment and activities. But as you could see, Northvolt is one of the investors. So there is a natural connection to a battery producer that could help us to produce sodium-ion batteries. But also we are open to any other lithium-ion battery producer. If they would like to produce sodium-ion batteries, this is still open and flexible to any collaboration and production. When it comes to patents, the good thing with sodium-ion batteries compared to lithium-ion batteries is that it still is an open field. So there are so many opportunities actually to patent new materials and new methods and so on. But it's a fight also that everyone is trying to get its own patent, and so it is challenge. It has been a challenge, and it is challenge, and it will be a challenge, I think. So what we do is we try to do our best to get the right pattern on right timing. Otherwise, yeah, I don't see any other solution for that.
Yeah, I was wondering that sometimes one hears about keeping trade secrets, which may be a strategy not to publish the data. But I was wondering whether in competitive topics like this one, it could be an option. But I don't know enough about it.
Yeah, I would say we have both the strategies. There are some secrets that are not patented, We try to keep it secret as much as we can, but there are things that are patented. That means we try to protect them via having the patents. So we will see where we will end up.
Complex.
Yeah.
Well, thank you. Great talk. Thank you.
Okay. Yep.
Thank you. So I wanted to know, during the Prussian-wide synthesis, it's pretty easy to get the iron oxidized and have mixtures of Prussian blue and Berlin green. So I wanted to know if you have studied that, how have you achieved the purest Prussian white, and how does it affect like this mixture with these other analogs?
I agree with you that it's challenging, that it's easy to get mixed Prussian blue, Prussian white. I can say that it depends very much on the precursors used, on the synthesis conditions, temperature, and the way that you synthesize. But that's all I can say. Unfortunately, I cannot go more details of that. I mean, there are patents out by Aldis and also by other companies, which might be interesting for you to look at it. But there are, of course, details also that people don't talk about it.
Sure. Thank you.
Okay, we have a question online. Yeah. Okay. Yeah.
Hello, can you hear me?
Yeah. Alexandru?
Hello. Yeah, can you hear me?
Yes.
Yes, yeah, very nice presentation. I really enjoyed. Sorry for not being there with you. But yeah, my question was about this, also the solubility. So when you check the solubility, did you check it in solvents or in the electrolytes? Because I guess there's a difference when you measure solubility in pure PC or in PC that already has 1 molar of lithium of this.
You are right. So when we did ICP to measure solubility, this was on solvent, only solvent, because otherwise it would be extremely difficult to measure solubility of lithium fluoride in real electrolyte. But when we did electrochemistry, where you could see clear connection or relation between the solubility, capacity loss, and the volume, everything, of course, was a real electrolyte, 1 molar sodium PF6 in electrolyte. When we did mass spec, this was real electrolytes coming from cells. So there was 1 molar PF6. So that's why also it's very difficult to assign the peaks to a specific compound. So we had to just trust the differences that we see between the different peaks.
Okay, good, thank you.
Okay. We have another questions. Maybe I might take advantage to have one. So did you actually see do you have a clear trend on what is controlling the solubility? So for instance, you have higher solubility in PC than with ECDC or ECDME. So what is the main parameter at play there for the SEI solubility?
I guess the interaction between the solvent molecules and the salt and the coordination which is formed, because ultimately it's going to be dissociation. Even if sodium fluoride or sodium carbonate with a small solubility, there will be some dissociation between the cation and anion, and then there will be interaction between the solvents and cation and anion. So I think that's ultimately the factor which will define the solubility. But it is, I can say that also we do see for sodium fluoride and lithium fluoride and carbonates, you could see that there's a clear trend that the solubility is increased from lithium to sodium. But there are examples that it's opposite. So that's also adds to the confusion.
Bob is a nice example.
Bob is an example that, for example, lithium Bob is more soluble than sodium Bob. Yeah.
Okay, thank you very much. Yes. Oh, okay. Sorry, I will go for the closer one.
Hi, Reza. Very nice talk. Thank you. You mentioned when you explored the different sodium electrolyte formulations that maybe TFSI in ECDME was behaving the best, like was the lowest capacity loss. Do you have any idea of which kind of SCI is forming? Have you like any compounds? Like you mentioned maybe inorganic is not good, or yeah.
We have done XPS to understand the differences between, between different SCI forming these electrolytes. In principle, you can see that yes, when the SCI becomes more organic in these systems, at least, it's becoming relatively more stable. But then again, XPS comes with its own challenges also. So this is ex situ measurement. The samples are exposed to, as you know, to cleaning, washing procedure. So there's always question on the interpretation of the data, but there's a clear difference that the SCI becomes more organic and more stable. That is, I think, one reason also that many of these additives used for sodium-ion batteries or in commercial cells, basically they work to form a bit more organic SCI with longer chain that have lower solubility also.
If I can still ask one more question, still online, Alex online from Belgium. Can I? Yeah, about this, the use of TEP and LIBOB. What is the concentration of LIBOB and TEP you use? Because this TEP, TMP are known to not be quite stable at low potentials.
Yeah, sodium bob in TEP.
Sodium bob, sorry.
Yeah, so you could dissolve them easily up to half molar, 0.5 molar. If you go TMP or TEP, if you mix them with NMP, you can go even higher, like to 0.8, 0.9 also. But not more than that.
But then in your electrochemical cells, do you use like 0.5 molar sodium bob in TEP, for example?
Yes, for the electrochemical measurements in unoptimized cells, yes, that's the base electrolyte.
And you can cycle carbon in this configuration with this electrolyte.
Yes.
Okay.
That was also one of the interesting things. If you look at non-flammable electrolytes in literature, often people use high concentration electrolytes to make electrolytes non-flammable. But here we found that actually with low concentration, you can have functional hard carbon with a non-flammable electrolyte.
Okay, interesting.
Which we think is becoming, because Bob is passivating. If you go lithium literature, people were saying that Bob is too passivating. This is not good. But when it comes to sodium, maybe this too passivating actually is good for hard carbon.
Okay, nice. Thank you. Thank you again.
Yeah, thank you for the nice presentation. My question is actually based on the sodium and lithium comparison, like the obtention based on the ore, because you said like you have carbonate ores most of the time when you present this, and I know for sure that there are other ways to obtain as well sodium and lithium. And my question is, are the process somehow equivalent, saying that for the same amount of, for example, ores, you would get the same amount of sodium or lithium? And is it as energetical equivalent, let's say? Because sometimes you can say, okay, we have more sodium ore, but it's much harder to get, and the yield is very low.
It's a good question. And to be honest, I don't know, because this is not my expertise. I don't know very much about mining and raw materials, refinement, and so on. But it's definitely a valid question, because it's not only abundance which will define the ultimate cost. I guess one good example is magnesium. As far as I know, magnesium is not that cheap for different reasons, while it's one of the abundant elements. So it's like many different things which will define the ultimate cost. I agree with you. But one way for people like me who don't know the details is to look at the ultimate price. So when you look at the carbonates, sodium carbonate is cheaper than lithium carbonate. And I don't know how they are produced, but ultimately it's cheaper. So that's how it is today. And if you say that you can make battery materials from other sources, it doesn't have to be carbonates or hydroxide, maybe you're right. But then again, I don't know those. But as far as I see, carbonates and hydroxides have been, at least so far, the most common precursors for the synthesis of cathode material.
Thank you.
Okay, maybe one last question.
Hi, it is a nice presentation. Thank you. You did your studies on both high surface area carbon and low surface area hard carbon. I want to know how surface area affects the process of.
So we did work on low surface area hard carbon and high surface area carbon black.
Yes.
And of course, it was very, very clear difference. You could see that this capacity fading or capacity loss when you pause the cell is of course much higher when you have higher surface area, which again goes back to the that we actually intentionally accelerated this issue by having high surface area and large volume of the electrolyte. So there is a clear relation.
Okay, thank you.
So we expect that in real cells, when you have low surface area materials, this will be less problem.
Thank you.
Okay, so yeah, maybe we'll end up here, except if we have any urgent question, but Reza will be here also tomorrow for the jury thesis of Juan Forero Saboya. So he will stick around for some time. So you might have another opportunity to come and discuss with him. So you can send me an email if you have any urgent question and we can arrange a meeting.
Sure.
So thank you again, Reza. And yeah, see you tomorrow as well.